let's start with something about me. So I love programming, okay, and I like to learn different languages. So far these are the languages that I know. So they are sorted as per the proficiency I have in that languages. And Java is a recent addition. Earlier I used to work on C++, now I'm working on Java. So how many of you do object-oriented programming for living? Oh, quite a few. Then you would be surprised to see that. I'm not saying this. So who said it, by the way? So this guy, Alexander Stepanov, he used this phrase in one of his interview, okay? So that particular question answer thing is available on c2.com, and but it became so famous that there were like comments by Björn Stroustrup of C++, then some Java guys and that. So all sort of thing is there. You can go and visit this link. And the full interview is available on this stlport.org. Okay, so by the way, who is this guy? Who is this Alexander Stepanov? So this guy is a Russian mathematician. So as a by training he is a mathematician, but he's a programmer by profession. And he's really like, currently he just, I guess, retired from A9.com, the subsidiary of Amazon. And he's an advocate of generic programming style, which he and David Musser, they coined in the term generic programming, obviously in C++. So, and this guy, he designed a most awesome library ever done in C++, okay? That's a standard template library, which is the standard library of C++. And wrote 2 fantastic books on programming, Elements of Programming and From Mathematics to Generic Programming. So I have read the Elements of Programming and it's awesome book, okay? You should read it. So what exactly was he saying? So the question was, I think STL and generic programming mark a definite departure from common C++ programming style, which I find almost completely derived from Smalltalk. Do you agree? And what Alex said? Yes, STL is not object oriented, blah, 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 blah. Lots of cluttered thing, right? So let's filter it out. And that's the important takeaway from this whole paragraph, okay? He says, it attempts to decompose the world in terms of interfaces that vary on single type. Okay, that's the first statement. And the second statement, obviously you would guess, that's about functional programming, right? Multi-sorted algebra. Yeah, he's saying a multi-sorted algebra, that is family of interfaces that span multiple types. Okay, so what exactly is talking about? So I googled about it, and actually he is talking about data abstraction, okay? The data abstraction techniques that are used in 2 different paradigms. So what exactly is the data abstraction? It's a technique for defining and manipulating data in abstract manner. So you don't really have a specific deal with specific data, but you have a conceptual view of properties of data, okay? So an abstract type, okay, it can be a type that is conceived apart from the concrete realities. So an abstract type could be something like color, okay. The concrete reality or could be red, blue, green, right? But when I say color, it's abstract type. What you get from it? Nothing, right? Then let's see those 2 things again. So the first statement, it's actually OOP, okay, object oriented programming. And the second statement is abstract data type. So it's actually he's pointing to these things, okay. So and I will be calling them as ADT. So for next 1 hour, when I say ADT, that means abstract data type, not algebraic data type that is used in functional programming. Okay, we'll see some algebraic data types, but I'll point out that they are algebraic data types. So when I googled again, I found this awesome paper on object-oriented programming versus abstract data types. Okay, so it's by William Cook, and it's really awesome paper. You get nice basic things about ADTs and OOP things. So it's actually obviously the core of this talk. So what we gonna do next? So what we're gonna do next is we will try to implement same problem using objects and the ADTs. Okay. Then what we're going to do is we're going to apply some different criteria, like extending this design by adding new data types, okay, or by adding new functions to them. Then finally we will also check the optimization, where we can achieve more optimization or less optimization because of some constraints. So that we're going to see. So first part, implementation. So what we're going to do is we're going to implement a integer list, okay? Very simple. I'm not going to go generic and all. It would be a list of integers, list like 1, 2, 3, 4, that sort of thing. So if I'm an object-oriented programmer, okay, I think like, I want to write a list. So what I want this list to have? So I start with procedures or methods or member functions, right? So I would say I want to know whether list is empty or not, which will return a boolean, okay? Then I want to know the length of the list, right? Then, these two functions are like functional programming, you must be knowing. But head is like I want to know the first element of the list, and tell is I want to know the rest of the list, okay? So I first define an abstract type. So this is sort of interface, okay? I haven't defined how is empty is defined. I don't know what length is going to return, how it's going to return, I don't know. What is the list? I don't know. So this is abstract type. And these are the observations on the list. The things or the attributes or method, okay, I am interested in. So that's how we define our abstract type in OOP, okay. Then we start implementing some concrete representations. So one of the concrete representation could be a list could be either empty or say non-empty. So let's implement an empty list. So you see, I am adding columns to this table. So empty list. An empty list will always, so these are like implementations sort of for how this program should behave. So an empty list is supposed to return true. When I ask him, are you empty? So it always return true, okay. Length, it's an empty list, so 0. What about head and tail? These two methods will not be, I am not going to define them. So maybe I will throw an error. Maybe, I don't know, if I am doing this in Python or something, or if I am doing this in Ruby, I will not add these methods at all, right? And I can get no attribute found error or something like that sort of thing would be thrown, right? So I'm not worried about the head and tail because obviously they are invalid functions. Now I'm adding another concrete type. So I'm calling it as linked list. What it does, it takes an int, okay, and takes another list. So can you spot? I am specifying the abstract data type list over there. So for the linked list constructor, the list could be either an empty list or a linked list or anything else, I don't know, but it's going to be a list, okay, an abstract type. So this linked list is always going to be non-empty because at least there would be one integer, okay, that data. So is empty would always return false. Even if it's a singleton list, at least I can create a singleton list out of it. Like a list, it contains say any number and the next list is actually an empty list, okay. Then length. So I am using over here some sort of recursion, but if you are doing it in Java or something, you are scared of recursion, use while loops or something like do whether the next list is empty or not, that sort of thing you can do. We are not going to go into specifically into the implementations of the thing. So I am using recursion on object. So I am calling simply length on the next object, okay, that I have. Now the head is going to return the data, right, and tail is going to return the next list. So next list could be either, I don't know, it could be a linked list or it could be an empty list, right. So that's how this is called as basically a specification matrix, okay, how my functions are, how my functions will behave in different concrete implementations. So that this matrix will specify, and currently we are considering only unary functions, okay, we are not considering any binary functions like equals or something where we use two lists or something like that. So for the unary thing, this is okay. For the binary you need another dimension. So possibly you have like two things, two empty lists and over here and all. So it's a bit complicated and I don't like complex things. Okay. So can I add more implementation to this? Yes. You can add as many as you want. Go to infinite. You can implement this list interface wherever you want and how many, as many times as you want. But Can I add any more methods into this list? No, this is a closed interface, okay? I cannot add any more methods to that. So adding a row to this table is big no, okay? I cannot add. Theoretically, I cannot add. Otherwise, you can go and open your class and put any methods you want. But theoretically, you should not do this, okay? So I'm not going to show you real implementation. Since most of you are OO programmers, you know how I implement this in Java. I will create a abstract list class, or I will create a list interface, then I will have an empty list concurrent implementation, then I will have a linked list concurrent implementation. That's it. Let's move ahead. So remarks. So primary mechanism of abstraction over here is a procedural abstraction. So that means the abstraction is I want to hide this stuff, right? So the data is abstract. I can't see the implementation because I am accessing it through some procedures. I am not really going to check that what's the type of that thing, and I can see only four procedures or whatever we had defined in our interface, right? So I cannot go and really check what exactly the real data is over there. Is it an empty list or is it a linked list? I don't know. All I can ask it is that, are you empty? What's your length? Give me head, give me tail. That's it. So that's why data is abstract, because you can't see it, and you can see it only through the procedural interface that we define. Okay. So PDAs, that is procedural data abstraction. Now in his paper, William Cook uses this term PDA because he says object doesn't really signify anything. Okay. So where in object orientation, where we are using this sort of procedural abstraction, let's use a term PDA, okay, that is procedural data abstraction. So for so on and so forth, if I use the term PDA, just replace it with the object, okay. So PDAs are organized around constructor. What exactly is that? So you have some interface, an abstract interface which defines what all methods you can call on the object, right? So the constructor or the concrete implementation of that class, it actually gives definition to that method. So the constructor of an empty list, it decides that the is empty would always return false, while a constructor of a linked list, which is a non-empty sort of list, okay, it will always return is empty will return true, and for the empty, and the linked list it will always return false, right? So this is decided by the constructor that we provide, okay. So when we organize our problem in terms of constructors, so different constructors provide different definition. Even the same goes for the data implementation. Empty list would not have any data members, right? But linked list will have at least two data members. One is the data and the another one is the list, which is the remaining, the next list, right? So observations on that data, that means the properties I want to access, they become attributes and the methods of that procedural data value, okay. So if you go for if you go into Python sort of programming, where you don't really have interfaces, okay, so you just design an object, or if you do some sort, if you have done JavaScript, I hate that thing, but you can create a JSON, okay, and inside the JSON you have one key, and it actually, there is a function which is assigned to that, and you create object out of it, okay. There is no class, right? So a procedural data value, that is that JSON object which contains some keys and some functions, okay. So I define, okay, as a combination of all sort of functions, all sort of say public functions that I can call on it. So those become the observations of that. Now let's move to the other paradigm, implementing an ADT, okay. So I'm going to implement the same linked list using abstract data types. So now you should have really keen eyes to see how I'm populating my table. I'm going to populate the same table again, but using different method. So I start with the abstract data type, right? It's a list. Those are different names, okay, but it could be either nil or it could be a cons, right? So I have defined my list in terms of types. So this becomes the abstract type, the list, and you got some concrete types, right? It could be either a nil or either a cons. So this sort of thing is known as algebraic sum type, okay. So my list could be either this or that. So this is a particular example of algebraic sum type. Okay. Now, once I have defined this thing, my abstract data type, okay, I go on defining some observations. So here you go. I can put observation called as nil, which takes a list, returns a boolean. Okay, that's a Haskell syntax. That's how you declare a function. So it takes a list and that arrow indicates that it returns a bool. Okay, and if it is a nil, you get true. If it is a cons, you get false. I'm going to show you the implementation, how exactly these things come. Okay, same for the length. The nil, it always returns 0, and cons, that's a recursive implementation, 1 plus length t dash. Okay, so because a t dash is a next list sort of, the head, it will throw error. In Haskell you can do that, or you can have some safe head or something which will return you an option. We are not going into implementation that deep. So, and the cons will return you x, the first element, the head. Again, when you implement tell, okay, you get a list and you pass a list and get a list. For the nil, it's error. For t dash, it's for the cons, it's always t dash. Now, can I add any more operations to this? Yes, you can add as many rows you want to this table. Okay, so in the PDA, the other implementation of the list, you must have seen that I had populated my table column wise, right? I had first decided that there would be 4 rows and 1 list type and the 4 rows of function, which like each row contains 1 function, and then I go on adding columns. Now you see that I started with a type, okay, and then I am adding rows. So simply you can add as many functions, you can define as many functions on your data, okay, but can I add any more concrete types? Well, no, you cannot add anything. Once you define that type, it's done. You cannot add any more concrete types to that. Okay, so I'm going to show you the real implementation using Haskell. I'm going to show you some code. So my Haskell module will look like this, right? So this is a list, is all the artifacts it returns. Okay, this is my data definition or the declaration, you can say. So this is a data int list which could be either nil or cons, and cons will take an int and also take an int list, right? So that's an abstract data, and those are the concrete representation. I'm using derived show because I wanted to print it on the console. So you can use something like deriving show or something. Okay, so show is a type class. So Haskell will automatically make your int list to be printable on the console, so that actually you can convert it into a string or something. Okay, so it's like toString of Java. Now I got some constructor functions. What they are exactly? If I want to create a nil list, I will make call make nil. If I want to make an cons type of list, the other list, I would use append to function. So why I need to do this? Can't I directly call nil and cons? Well, yes, you can if you export your data type outside of the module. So currently in my declaration of module, the int list, if it is followed by like say, this is a Haskell specific thing, okay. If I have something like int list bracket dot dot bracket, okay, that means the declaration of this constructor, the definition of this abstract type is also visible to the client of my module. Otherwise it's not. So currently my client can only see an int list. He doesn't know what is nil, what is cons, and he doesn't care, okay. He knows how to make a int list. So if you want to make a nil list, he doesn't care what exactly nil list is, but he can make a nil using this. And another non-empty list, he can make it using append to. Okay, so they were like constructors and the data. Now the operations, okay. So first, head. Head will take an int list and return an int. And what is this peculiar thing? I got 2 definitions for head. Yes, Haskell called this as pattern matching. So there is a definition for head when I pass a nil list to it, okay, and it will call an error, it will return an error. Or there is a definition for head when I call cons, list to it, and I will return a head. This is pattern matching where the underscore is, I don't care about what underscore has, because I'm not going to use it. So I'm going to simply return the X over there. So it's really similar to what we can do with in Java using instance of thing. Okay, I can simply ask what's your type, right, and take an action on it, because I can simply cast that thing and all that thing. But ideally you should not do it in Java, because that's an object orientation, and you should not ask type of object, because you don't know. You may have a countless implementation of your interface, and if you implement for 4 implementations, say, there could be a 5th implementation for which your program will fail. Okay, so when you do OOP, never ask what's your type, because there could be many. But in functional, you know that I first define that my list could be either nil or cons. So that's why I can have this liberty to exactly ask that object or data, what's your type, and take action based on it. So over here, again for tel, same. If it's a nil, I'm throwing. If it is a tel, I'm simply returning the XS. Okay, that's a style of Haskell, that you have X colon XS. So XS is the remaining, the next list. For the length, same. For nil, I'm returning 0. For cons, I'm returning 1 plus length. So in case of same for nil, I'm doing that. If it is a nil, true. Simple. Okay. So every time I'm just asking, what's your instance? Means in English, like what's your type? If it's a nil, I return a true. If it's a cons, I return false. That sort of thing. So some remarks. So primary mechanism of abstraction over here is a type abstraction. Okay. That means the real type of my data is not available to user. Okay, that is an opaque type. So I am not exporting definition of my int list outside my module. The client of my module won't be able to know what exactly, which exact int list he is dealing with. So ADTs are organized around the observations. What really is that? That means I can have as many observations as I want, and from where these observations would come from? Observation come from specific use. We're gonna discuss this particular thing in the next section in very detail. So just keep in your mind that it's organized around the observations. Okay. Now, each observation defined as the operation upon the concrete representation derived from the constructor. So you know that, as we have seen, each operation like head, tail, they were defined on the concrete representation, right? Constructors are also defined as an operation that create values in representation types. Yes, we have seen the make nil and the append to. They act sort of constructor functions. They construct the real data for me, right? Which is referred from the abstract data. The representation is shared among operations but hidden from the clients of ADT. You have seen that my operations, okay, all the operations that were defined in my module, they exactly know what the list is, right? But my client, since I am not exporting it, what he can do with that int list? He can simply say is empty, head, tail, length, that's it. He cannot do pattern matching on it, because I am not really telling him what's the real type of list it is. Now, we're going to talk about the extensibility, and I'm not going to take lots of time on extensibility, because people already know and we have already covered how we can extend the things. So, and you must be knowing the expression problem, right? It's related to that. So, I'm just going to show you some summary. So, OOP, new concrete representations of the abstract data can be added. You can define as many concrete classes you want, okay, implement your interface 1,000 times, billion times, it's okay. New operations cannot be added. You cannot, once you have defined an interface, theoretically, you should not add any more operation to it. You should not open it, because you don't know where your code will break then, because you don't really know that where this interface is implemented. Now, the ADT. New operations can be added, as many operations you want, wherever you want, right? If you know the representation. Concrete representations cannot be added, because I define my type as a closed type, right? I cannot add any more concrete representations. Now, there are few things. In OOP, you can always extend an interface by defining new and extending it from the previous one. So I want to add a method to my int list, say equals. I can create a new interface called as int list equals, which implements the int list, right? That's easy. I can do that. But again, I have to implement separate concrete classes for the int list with equals, which will extend from that previous classes and implement this interface. That all complexity I have to deal. Okay. And in ADT, you got something called as type classes that we're gonna see. But type classes, they are more or less like interfaces. Okay. So you will get all the hairy problems of interfaces when you start introducing the type classes and start implementing something like what we do in OOP. So we are moving again ahead to the optimization. Optimizing the ADTs. Since I already know what kind of data I'm really dealing with, optimizing an ADT is really easy. Okay, based on the concrete type, I can decide what can I do with the concrete type. So here is example. So this time my int list is actually can be a nil, it can be a cons which takes an int and another int list, that is sort of linked list, or it can be an int range. So what exactly is int range? So I am defining it as something like this. The first int that you take is the first number into your data, okay, and the word is actually how many times you want to increment it. So if I say 1, 2, the list would be 1, 2, 3, okay. If I say 1, 0, the list would be 1, right, because 0 times increment, I am not incrementing it at all. So that sort of, so I am calling it as int range, okay. So what I am exactly doing over here, instance equal int list where EQ is a type class provided by Haskell, okay. And what does type class actually do? Basically, they have some very abstract and some essentially common thing among multiple objects, right? So something like I want to compare two objects whether they are equal or not. I can do that with two integers, two string, two lists, two anything like two cars, whatever, right? So it's a very common trait, right? Very common trait. So that's what you do in Scala. You implement a trait, or in Rust you also have traits or something like that. So it's similar and it's equivalent to the interfaces of Java, okay, but not really they are like interfaces. You don't need to put that over like deriving show, yeah, that sort of thing. You don't need to do always with these things. So you can add as many type classes, you can instantiate as many times as you want. So over here I am implementing instance of EQ of int list, okay, you call it like this. So instance of EQ of int list where this is the equal to method, okay. So this EQ type class, it gives me two methods, one is equal to and another one is not equal to, but they are defined in terms of each other. So if I provide one implementation, the other implementation would be like inferred from the previous the previous based on this implementation, okay. So since I can actually inspect the type of the list, right, I can say equal to of nil and nil, yes they are true, I know the type, they are same, they are true. Equal to of anything and nil, well it's false because one list is nil and another could be anything. And this is a like particular feature of pattern matching, that first it tries to evaluate the first pattern. So if the both lists that I am comparing, if they are not nil, then it will try to match this pattern. So over here the right one is a nil and the left one is actually, okay, this left one, that right one, okay. So it's actually a non-nil, so it would be false. Again, if it is a nil and anything other than nil, false. No, this is nice thing, okay. Just consider that if you want to perform, we're gonna see what could happen when I want to compare two int ranges. Over here, since I can see that thing is, it's a nice int range with f1 n1 and f2 n2, I can simply say that if f1 is equal to f2 and n1 is equal to n2, then they are same, Okay, so this is a constant time operation. See the how optimization, see how we are achieving the optimization over here. So we are not really inspecting all the things because we can see the type, and based on that we can say that yeah, if they will be equal if f1 is equal to f2 and n1 is equal to n2, right? Next, this is a very generic thing. If all the specific things fail, then I will go to my generic solution where what I am doing, take a head is like you can have something like you can bind the variables like this. Okay, so head 1 is actually head of list 1, head 2 is actually head of list 2, tel 1 is tel list 2, tel list 1 and tel 2 is tel list 2. Okay, so what I am doing, I am checking if head 1 is equal to head 2. Okay, then go and check tel 1 and tel 2, but if they are not, then I will simply return false, right? So that's a basic solution, that how I am going to compare two lists. I will compare the two elements of two lists. So that's a very generic solution. But see over here, since we can actually see the type, we are not performing any operations. We are simply detecting that, okay, we are simply saying that this is a very small constant time operation. This would be linear, right? So always constant time operation is better than the linear. Now, in case of PDAs, optimizing operation is difficult because representation of the argument cannot be inspected. So I really don't know what kind of list I am dealing with. What I can do is I can simply ask him, are you empty? Give me your length. That's all I can do. So here is the implementation. So here is our interface list, and I am going to implement that check if equals, okay, where we take another int list, okay, the right hand side int list. Okay, and we try to compare whether it is equal to my thing or not. What I am going to do? I am going to do compare every element with each other. So while LHS is not empty, RHS is not empty, I am going to check the heads. If head don't match, return false. Otherwise, move to the tail. Then and go on doing this loop until one of the list exhausts, and then you come over here and where if LHS is empty and RHS is empty, that means both lists were of same length, okay, and still that head is not equal to head, it didn't return false, that means really both lists were equal. That's how I do in object orientation, because I can't really ask int list, assume that I don't have instance of, okay, I can't really ask what's your instance, and there is no use of asking it, right, because there could be infinite implementation theoretically. How my function would grow like anything, so it would be beyond any optimization if I do that. Okay, and consider what if your int list, actually what you are doing is list 1, the concrete implementation are int range, you have an int list of million elements and another int list of million plus 1 elements, okay, actually million plus 1 and million plus 2, okay, and what you are doing is list 1 check equals, you are going to do million combinations before you find out that this head is not equal to that head. So this is like linear complexity problem, which could have been a constant time complexity if I would have been known that there is an int range. Okay, so pragmatically speaking, what you can do is, okay, if you are in your concrete implementation, just check the instance of other thing. If it is not, then use a fallback strategy. Over here you can save something and you can have good optimization over there, but not really as you can have with the closed data types like you have in ADTs, right? So that's the final part of my talk, okay? Tyranny of dominant decomposition. What exactly is that? Actually, I am going to talk about that first statement. It attempts to decompose the world into objects that are varying on single interface. Let's see how. The limitation of OOP is that one has to choose a fixed decomposition of the system in the design of class hierarchy. You start designing a hierarchy, you have a very basic interface, then you refine it further, finally you have your implementations, right? So you follow this tree like hierarchy when you define your system in terms of OOP. And here's the example. There is like I want to classify trees and say plants, okay, from two different views. So if a lumberjack is there, he would say that a tree could be either a hardwood tree or a softwood tree. So finally if these are the implementations, don't judge me by my botany, okay? I don't really know whether what is a hardwood and softwood, okay? This is just example. So hardwood, a cherry would be a hardwood implementation, a mahogany would be a hardwood implementation, similarly mango is a softwood, pine is a softwood. That's how a lumberjack would decompose this thing, based on the, like he want to check how the wood of this tree is. But if there is a bird, he could decompose this based on food, right? He could say again, these 2-3 plants are actually nectar plant, okay? So I can have, I decompose them like this, and there is one which is an insect plant, okay? There I can find more insects. So it decomposes this in this way. So you have same objects, same entities, okay? But there are 2 ways of classifying them. And the problem is, if there are 2, there could be third, right? There could be a botanist who would classify them altogether in different manner. There could be a person who would classify them geographically, that a cherry, a mango is found in somewhere in India, or a mahogany is found somewhere else. That's possible, really that's possible. So what you gonna do? And I cannot go and adding hierarchy again and again. Suppose I came up with these 2 views, and cherry is now implementing hardwood as well as a nectar plant. What you gonna do for the third view, okay? Are you gonna open your cherry class again and implement the next interface? No, you're not going to do that. So that's a problem, right? And how I solve it using ADTs? Well, I have type classes. So in object orientation, what I do is I try to classify. I first see object. I start with the class, okay? So there is, if I am asked to solve a problem, if I am asked to design a list, what I would do? I will start with the interface list with 4 functions. Wait, man. What functions you want to use out of them? Where you want to use them? Well, I don't know, but list should have those 4 functions. That's how I start with the type start with the OOP. But in case of ADTs, first I start with a use case, a nice use case where, okay, a use case of a lumberjack. Okay, so that class is a Haskell type class, okay? That's not a Java class or something like that. So a Haskell type class tree, okay, where you have some tree functions which would have operations defined on tree, or some you want to get some attributes of tree, something like that. Then you could have a more refined case of a hardwood tree, right, where you could have some of the hardwood functions, like how much strength you require or something like that, I don't know. Then there could be a softwood implementation, right? So these are more refined, and this thing, you know what, this is sort of extending the interface, okay? So hardwood actually accepts a tree, okay, and softwood is also tree, right? So this is sort of inheritance, you can see, okay? Similarly, there could be another use case where I want a plant. So similarly, I can define a plant, okay, then I can define a nectar plant, I can define an insect plant, and they would have their own methods and observations which they want to derive from the data, right? So far I haven't thought about what exactly my cherry tree or my mango tree is gonna look like. I don't really care. I am talking about what I want from it. Like when I say EQ, like equals, so I want equality. I want to compare 2 objects of that class, okay, or of that type, right? I don't really care about what is that type. When I say EQ A, that means A should implement an EQ or instantiate an EQ type class. That's what I want. So like that, I want to see these functions. So they are very similar to the interface of Java, okay? But now it's little bit different. So I start with a tuple, okay? So that's like aliasing of type. So some cherry attribute is actually a tuple of int string. And you know what? That this tuple is actually algebraic product type, okay? So over here the cherry tree is defined as some cherry tree constructor and some cherry tree attributes, right? And I'm not going to define the module part and all that, or that's all understood that, okay? Then the place where I want to use the cherry tree, okay, if I know the exactly cherry tree where, or I can simply implement the hardwood or instantiate the hardwood type class for my cherry tree, and tree function 1 may return the first or second attributes or something like that, right? So I have some data with me, okay? The functions actually they are attempt to access that data. Those are observations on that data. So I want to access something from that cherry tree, and my cherry tree in my file, it will define, oh, you want to access tree function 1, okay, you want to access hardwood function, okay, do this. So these definitions are provided by me, the implementer of cherry class, okay, or the cherry data. Similarly, I can have another instantiation of, say, nectar plant, and I can provide functions like sweetness and plant function based on the cherry tree implementation. So whoever wants to use the hardwood or a nectar plant type classes, does he really needs to know whether he is dealing with the cherry tree or a mango tree? No. It actually depends on when you are calling and if the cherry tree is really implementing the hardwood or not. Otherwise the Haskell type static type system, it will throw on you, okay. So that was the theoretical example, like who gonna go and check that whether I have there would be a nectar and this bird view and there would be a lumberjack view, right? So let's take a real life example that me and you, we are using it every day. Can you recognize this hierarchy? It's a collection hierarchy, okay? I don't know whether this is correct or not. I just downloaded it from here. I'm a new Java programmer. I just downloaded it. So what I can see a list interface which has some functions. They are very blur, okay? Then there is an abstract list implementation. Then there is a vector, then some stack, array list, and abstract, sequential, something, and a linked list, okay? Then there could be a queue or something, I don't know. It interface the DQ interface or something. Let's focus on this part, the list part, okay? So, like we defined something in OOP, we started with the list interface. Then we provided some concrete implementation. So forget about these middle things which are incomplete abstract stuff. Look at this vector or array list or linked list. What are they? They are concrete implementations. So a vector is, when I look into documentation, they say that it's a random access list. It contains something of T of like an array inside, like array list, but it is synchronized or something. Okay. So these are two implementation which have an array inside them. Okay. Then there is a linked list. This is a different one. You got nodes and they are linked together, right? It's a doubly linked list, right? So we got these three implementations, correct? So if you see, this decomposition is based on only one thing, what thing I want to access from this list, right? Am I considering how I want to access them or what really I want from it? Let's take a quiz. Tell me, is some function or is of quadratic complexity? Can you tell this? Can you tell me? Well, you can't, because you don't know the underlying implementation of list. Which exactly, are you dealing with array list, are you dealing with vector, or are you dealing with linked list? You don't know. So if it is a linked list, get gonna be a linear operation and you are doing it inside a for, it could be a quadratic, right? If it is a vector or array list, it would be something else, right? It would be, this get would be constant time operation because it's an array. You just jump into that index, right? So it's really fast. But what about, so it would be linear time operation, right? But it all depends upon, and I can see this at the runtime, because at the only runtime I would know that which exact implementation list I'm using, or on which real object the get is getting called, right? So that's a problem. That's really a problem for me. So I cannot say that what's the complexity of my operation unless and until I really know with what sort of real type I'm dealing with. So there could be a different view of looking at it, right? So I can have something like the way I access, right? What is the complexity of this binary search if you have seen this in collections? So binary search, if you go and see the documentation, they will say that if in case of list which is either a random access implementation, you got some marker interface called as random access, and you are doing instance of random access, then you are calling something where you can have really random access over that list, okay, because it's a vector and it's a array list, okay. Otherwise, if it is something else than random access, what you are doing is doing all sort of the linear complexity binary search. Look at that. Why I use binary search? Because I want logarithmic complexity. I have a sorted list and I am just jumping from here and there and trying to locate the variable I want, right? What's the use of it if I am doing it in linear way? I would use find, the linear operation, which might be faster than this one. So the problem is the binary search and this sum function, actually they want to categorize the collection they are accessing based on the way they want to access it. Not through the interface, not the what procedural interface they want, what things they want to access it. They want to access it in some way, and as a designer, I should get a chance to tell that, okay, over here I'm going to deal only with the random lists, random access list, right? Or I'm going to deal only with the linked list, that sort of thing. Well, when you decompose things into single fixed hierarchy, you cannot say that, because there is only one way, one view of looking at it, right? So, what could be an alternative? So this time, I'm not going to show you Haskell or something, I'm going to show you C++. Okay? So, standard template library in C++ is actually designed using ADT approach by the Alexander Stepanov, okay? So we have some containers which are like data structures, we have some algorithms, and we have some iterators, right? And obviously it's not OO, right? Then algorithms are defined using iterators, okay? So iterators, what are they? They encapsulate access to the containers. And what sort of containers I can get? I can get, say, a sequence containers like array, okay? It's a plain old C array, just a sort of wrapping. Then a forward list, which is a singly linked list, okay? Then a list, which is a doubly linked list, a vector, which is very similar to the array list, a dynamic array, and a deck, okay? Then I can have some container adapters. See, I am not using inheritance over here. There is nothing like collection interface or something. All these classes are concrete classes. They don't inherit from any other things. So for implementing stack, if you have remembered the previous slide over where the stack was implemented somewhere from the array list or something like that, like the stack was down here. No, we are using composition. We are using stack is actually containing some other container, okay, and it provides push and pop based access to it. And finally I have some associative containers like map, hash map sort of, okay, and some unordered thing. Actually hash map and these unordered set, they are hash based, and the associative containers, they are tree based, okay. But for this particular discussion, my interest would be the sequence containers. So let's say I have got these 4 sequence containers, a forward list, which is a singly linked list, a list, which is a doubly linked list, a vector, which is a dynamic array, and an array, which is a fixed size array, okay, and even I can have something like very basic C sort of array. Now let's see, I am interested in single pass algorithms, okay, something like for each. I just want a collection, I want to visit every element and do something with that, or a transform, which is like map, right? I want to take in collection and process every element with some function and return you another collection. Copy, find, rotate, all these things, okay, they are single pass algorithm. I just zip through the containers, right, all the containers. So in such case, I am not really moving back, right? So why I need bidirectional access? So I could work with the forward range concept, right, where I am just moving in one direction, I am not moving back. So here is one decomposition. I call all 4 sequential as forward range, right? Then there could be some algorithms with the bidirectional access, right, reverse. I start with that end and I start with this end, okay, I am swapping until I meet somewhere in middle, right? I want to access that collection from both ends. Is it possible with the singly linked list? No, that's really slow operation, okay? You are starting from this end and moving here, next till that end. No, that won't work. I want constant time access. Can I do that? Can I move from here and there like that? No. So obviously, the decomposition is something like this. The bidirectional ranges, the list vector array are bidirectional ranges. I can access them from both ends, but forward list, no, I can't. Again, the third view, random access algorithm, something like sort or binary search, okay? I don't want to do something like this, then move next, no. I just want to jump into the middle and check what is my element. That's it. So, again I decompose stuff in terms of random range. So, all the things like vector and array are the random ranges. This list, okay, it's bidirectional, but all list vector array. So I just tried to draw sort of Venn diagram, okay, to tell you how this concept, how I am refining it. So basic concept is single pass thing, okay, the forward access, forward iterator. Then there would be a refined concept called as bidirectional iterator, which could move in either sides, right? Then there could be a random access iterator which can jump from here and there. So if I want to do 4 paces, I am not doing 1, 2, 3, I am straight away jumping into that place. So that's how I achieve my decomposition. So there is one way where I have decomposed stuff based on structure. There is another thing, the iterators which decompose same data structures, okay, in terms of access, right? So if I want to do this in Haskell, same, iterators could become a Haskell type class and I would instantiate them outside. That's what is done in C++ over there in the standard template library. So we don't really have something like collection interface or something over there. So finally, the last thing what is remaining, actually I had decided that although this is a FP talk, I'm not going to use any mathematical term, okay, the boring things like monads and applicative functors and whatnot. I don't like it. I'm a stupid programmer. I just do coding. I don't like math much, okay. But for the last thing, and I haven't even created a slide for it, okay, I'm going to talk about algebra because the last thing that is remaining is the second statement that he had, multi-sorted algebra. Types that vary on multiple interfaces. What exactly is that? Well, if you are seeing the type classes, a type class, if I say that it's the interface, okay, then by instantiating multiple type classes, I can have multiple types, multiple objects which are varying or different interfaces. Now let's go and throw away the type class and all things. Let's go simple in the simple things, okay. Plus operator, addition. I want to do addition. I want to add two things together. What I can do? Can I add two integers? Yes. Two doubles? Yes. Two strings? Yes. So can you see there is an operation called as add, okay, and it is defined over some domain, okay. In mathematics, algebra or algebraic structure is actually what? It's a set of a domain and the operations defined on it, right? What if the domain or the carrier set that they call, or also called as sort, people call it as sort, okay. Actually it has multiple sort, like the addition. I can add int, I can add double, I can add string, and I can add whatnot. Wherever the addition operation is provided, okay, I can have that type in my carrier set, right. So such thing, such sort, we call it as multi-sorted thing. So that's it from my side. I'm not going ahead from this. That's it. I'm done.